Welcome to this challenging Newton's laws problem. What you will be challenged to do today is really be clear about what your system is, what your surroundings are, and how that shapes the corresponding free body diagrams. Notice this subtitle, inertial reference frames. That will also come into play, especially when we look at the free body diagram for the 10 kilogram block. Let's begin with identifying our systems. We're going to do M1 is going to be the 10 kilogram block, and M2 is going to be this bracket, okay, which also includes the pulley. So surprise number one for you may be how the FBD looks like for the bracket. Okay, I'm going to draw it for you and then we can talk about it. I don't think that so far what I'm drawing is any surprise. I'm going to call the normal force from the ground on the bracket, N2, corresponding to the force on M2. Okay, here's the surprise perhaps, right there. We have two forces to the right on the bracket. Okay, in other words, this string communicates a force to the bracket, but so does this. Strange, isn't it? And then finally, there's a friction force from the 10 kilogram block backwards on the bracket. Notice that our free body diagram is unbalanced to the right, so we would expect acceleration to the right. Let's continue to the next surprise. Now we're going to consider the 10 kilogram block right here. I have two free body diagrams for you. Similar forces in each case. Okay, I should point out that the force applied in each case is equal to the tension from the string here. My question to you is, which of these two free body diagrams is the correct one? This one on the left or this one to the right? Notice they're the same except for the amount of balance or lack thereof in the x direction. And the correct answer is that the one on the left here is the correct one, okay? And that is because from a perspective of somebody who's at rest on the ground watching this, they will see the 10 kilogram block accelerate to the right. And therefore, free body diagram should be unbalanced to the right. Now this can get really confusing because if you hop onto the bracket, right, and you observe things from here, you'll notice that the block with respect to the bracket is not moving. And so you might conclude that the forces on it should be balanced as we have in this right-hand free body diagram. But the issue is this. When you jump on the bracket, you're no longer in what's called an inertial reference frame, right? Which is the frame for which we need to observe things to see Newton's laws obeyed. If we want Newton's laws obeyed, we need to observe from a perspective of being at rest or moving at a constant speed. We've already determined that this bracket will accelerate to the right, so that's like being in a non-inertial reference frame. And so you start to see things in a non-inertial reference frame that aren't really there. For example, when you are making a turn in a car, you feel thrown to the outside but actually pushed to the inside. Let's conclude with a free body diagram for the two object system. Okay, very simple. We have the combined weight of both objects pulled down on by the earth. We have the applied force. And we have a third normal force, right, from the ground acting on the bracket and the block. There is one more weird thing worth mentioning here that's going on, right, which is that we have a static friction force acting for an object that's accelerating. I know that's counterintuitive because the word static means at rest, but what we mean is that the surfaces, right, are at rest relative to one another. Every time you walk to class, your foot is momentarily at rest on the ground as it propels you forward or we should say as the ground propels you forward. So that is also a static friction force. So notice there can be a motion even though there's a static friction force acting. It's the same force that works to propel a car forward when the car has proper traction and the wheels don't spin. Let's go to the last slide. What we use our existing free body diagrams to write F equals ma equations. So I'm going to pause and write some things out here so that you don't have to watch me slowly write everything. This is the most crucial skill, I would say, after drawing the free body diagram, is to be able to translate your free body diagram into an equation. Because once you've done so, you have transitioned from the physics concept to the math tool, and you can proceed with algebra or calculus to solve the problem. So in the x direction, M1 looks like this, and in the y direction, the forces are balanced. That's M1. M2 has that force acting on it twice. Then it has the friction force from the block acting backwards on it, M2A. In the y direction, a little more interesting here, we have the normal force on the bracket from the ground, right? And then we have the weight pulling down on Earth, on the bracket, but we also have the block, right, the 10 kilogram block, pushing down through a normal force on the bracket, and all of those balance. And then finally for the system, very simple, we just have the one force acting on both masses in the x direction, and then in the y direction, the forces are balanced, like so. What you have here in the end is you have three equations in the x direction, right? And they all have the same acceleration. So I leave it to you to solve this system of equations for both the maximum force that can be applied so that the block doesn't slip and what the resulting acceleration is under those conditions. Good luck.